Hey everybody, just trying some new stuff out here. Got a couple of requests for additional information. I also want to put more things out for 10 and 11 as we finish up our quiz here. I know a lot of you are working through it. I got to tell you a couple things. One, we were getting through chapter 9 and we're good. Now, you've all had at least one class before, and you should have had a lot of these Excel functions, knowing that anytime you have the INV in your Excel function, that gives you the inverse or value function. And if you have a DIST, that gives you probability. That's basic Excel 101 that you should get early on in a marketing class or your first Stat 210 class. And the hypothesis testing, and with that, the confidence intervals before that, a lot of these formulas from Z and T are in there already. So there is an assumption that you would have had these. I put stuff out for Chapter 8 for review on Learn Smart if you haven't had it. I can give you examples back to Chapter 8 and 9 if you need them, but it's kind of assumed that you'd have those in the second section of this two core sequence. So those things are going to be out there. So when we get into chi-square or chi-dist or norm dist or t-dist or f-dist or any of that stuff, those should all be straightforward, and then the imputation from them are straightforward with the values of alpha, degrees of freedom. X is a value that you generated. So again, it just keeps adding on. You have the foundation. It's not something you need to be reaching for. Moving on to chapter 10. I'm trying some new software here, so if you see this, I might put another one up, might goof this up here and then. I like to start trying to live stream some of this if we have time on maybe a Thursday night. But I'm using some gaming software. Maybe you'll see me playing some Othello or something. But just quickly on chapter 10, we're looking at two populations generating two separate independent samples. Now, they don't have to be the same size, but they do have to be drawn separately and independently. Most often, they're not the same size in real life. Unfortunately, in books, it isn't real life. You get a lot that are the same size. It's just easier mathematically. The other is something called matched pair sampling or pair differences, where you look at pre and post test. That is by far the most common kind of matched pair. The other is when we have something that's acted upon. So you have two real estate agents that are appraisers that are appraising 10 different homes, and you want to see, is there a difference in the way they on average appraise their homes. But it's one thing being acted on. So it's a pre-test, post-test kind of thing or something like that. There's a lot of different kinds of matched pairs. What we like to do is first talk about the difference between two means and how we draw that out with independent and random samples in this case. So we do have two separate populations. The samples that are drawn, they may be the same value, but they're drawn independently from one another from two separate sources. That's the clear delineation we have. Now the question is, these Greek symbols we keep seeing, you should have seen this before, but the mu's, the sigmas, the chi's, all Greek, they represent from the population as parameters. Again, if this class wasn't drawn samples to statistics, this class will be called parameters and not statistics. So we have mu1, mu2, that means of the population. We'll take samples from the two populations and create sample means, x bar sub 1 and x bar sub 2. They're our best guess at what's happening. Now, that one sample, we do just draw one sample, great, in each case. But the reality is, it's assumed that you would repeatedly sample over and over and over and over again and look at ultimately all the different samples and see how they work. Because if you drew an infinite number of samples that got all the possible combinations that exist for all the different sizes, you summed up all the sample means of all those, the sum of the average of all the averages would be the mu value. It's a lot. So we're going to look at the confidence intervals and hypothesis testing for mu1 minus mu2. What we're saying is there a difference between the two population means? We take the difference and set that equal to 0. Now those x bars do represent a point estimate, and we're going to float around those values an error measure, which is our z or t statistic times the standard error, and that will be plus or minus. We got to make sure, though, that we're drawing big enough samples. The sample sizes need to be at least 30. That gives us that interesting thing you learned about before called the central limit theorem. When that kicks in, you can assume that if you were to draw the mean over and over and over again randomly from the same sample, from the same population, and then plot all those means, it would look like a normal distribution, a hump distribution, or you might notice a bell curve when we're all asking, do we curve grades? Now there's three conditions when we do this. Do we know the sigma or not? You'll see here it says if we know sigma squared sub 1 or sigma squared sub 2, we use z. Anytime that you know sigma for both, you use z, just like you did before with the single sample. That's really not that common. I mean, if you knew sigma squared sub 1, you knew sigma squared sub 2, you have to think somewhere along the line you knew what mu was to get it generated. You can't get sigma squared sub 1 without drawing mu. But that uses a z distribution. It's not that common in real life. It's very common in what we do. The other is the one that's not common at all anywhere, and that's if we don't know the sigmas, either one or both, we assume they're equal. Well, that doesn't really happen all that often. You'd have to almost know what the sigmas were. And you can do it if you have the sample variances being very, very, very close. Rarely happens. What we do is we use something called a pooled variance at that point. That's what we see here, the s squared sub p. And that represents the same variance for both. So again, you'll be assuming the same variance, and we'll just work on different sample sizes. Don't know sigma, it's a t. The other one is when we don't know sigmas and we don't know they're equal. That's by far the most common. And actually, you can use that just about any time if you have large samples, because the s squared sub 1 and s squared sub 2, they'll become sigmas when the sample size gets large enough. So, confidence intervals. Let's talk about the first case when we know them. We have the difference in the means. We're going to float the standard error here. Notice it's additive. We don't subtract those because you have to compound the variability there, and you multiply it by the z statistic. If you capture 0 in that interval, that means that you're not finding a significant difference between the two. You're looking to get that range set up, in this case, so 1 minus alpha times 100%, sigma known. In the one that doesn't really happen at all, the pooled variance, you can see it's very similar here, x bar 1, x bar 2. We're using t in place of z, and now we're taking that pooled variance, and we're seeing what we can do with that pooled variance, and we have each of its independently drawn value for the sample size. It has its unique way of calculating the pooled variance. The nice thing about this is it has a really simple degrees of freedom. Sample size 1, sample size 2, minus 2. Essentially, it's n minus 1 plus n minus 2 for the two sample. Pretty simple. The last one, by far the most common, this is the one that has the convoluted degrees of freedom calculation. This is done in a sheet for you on Canvas, chapter 10. Just look for it. It calculates it for you. Same principle here. You're trying to capture 0 to find if there is a significant difference between the samples. The hypothesis test, as you've already seen from chapter 9, is that in the null hypothesis, h sub 0, all of the ones in the null have an equal in them. So equal to, greater than equal to, less than or equal to. The alternative hypothesis, there is no equality. Not equal, greater than, less than. Wherever the beak goes, to the right, to the left, lower tail, upper tail, and the other is two-tail. The statistic is very straightforward. It's just like the z we saw before, except that we now are taking the difference between the sample means and comparing them to a difference between the means of the two populations. It's assumed to be 0 in 99.9% of the cases, and you divide by the standard error of the two. That z statistic can be converted into a p-value, which then can determine whether or not there's a significant difference, significantly more or significantly less. Same thing for when we have it with the unknown sigma and assumed equal, really rare, but really nice because the math is easy. And the one that happens the most just happens to have the most disgusting amount of math for the creation of degrees of freedom. Again, t distribution, remember the t distribution is simply a version of the z distribution based on sample. Looks like the z, feels like the z, heavier tails, not as peaked. It just has a little more wiggle room because you have the variability of not drawing perfect population. Some kinds of examples, we're just trying to figure out if we can find a difference between two things. Here we're given two sample means. If you see me jumping around, I'm just testing out other kinds of software simultaneously in the background. Two different kinds of samples, brand A, brand B, to look at their nicotine content. We know the nicotine content of the samples. We're given a sample standard deviation, which could be turned into a variance. Sample sizes. Construct a 95% confidence interval. Now, we had this. We had it here if we wanted to. Here if we wanted to, I'm sorry. Or here if we wanted to. The one thing we have to know now from this is, what do we know about sigmas? Well, we know we don't have them. Now, when we do the test, do we assume that they're the same or not? Well, in this case, let's assume that they're unknown and they're equal. So you'd use the pooled sample size 20, sample size 25 minus 2 is 43. That's fantastic. So you know the pooled variance, you plunk it in, and you get a value here. The one thing I do want to point out right here is calculating these statistics. This is the part that's goofy about all that we do. Um, Tables are hard, and all of us that have been in statistics for a while learned on tables. Excel has made it a little bit easier because you can just go really quickly and it's repetitive. It's just that you have to know what to use when and where. And since I'm not holding you to taking tests without notes, you might want to start writing this stuff down as you go through the quizzes. Here you're looking to find the t-statistic for a 95% confidence interval. They've already halved it here. They're saying 2.5 in the lower tail, 2.5 in the upper tail with degrees of freedom of 43, and you get 2.017. Where does that come from? Well, what I'm saying is I'm taking an inverse function because I don't want a probability. It's a two-tail. Let Excel take care of the splitting, so we put the full 5% in the 43, and we get the 2.07. So it's absolutely doable. Jump back. So we're able to calculate something just like that here and get this floating value. Notice 0 is not in here. These are fully negative. So in this case, there is a significant difference. One is less than the other. We got to figure that out. Now, we're going to float another one, but let's see. What about the average between the two? Are they the same or not? So if they're the same, let's set them be the same. You might want to take mu1 minus mu2 equal to 0 here, and the other not equal. This is a two-tailed test. 0 is not in there. Guess what? Reject the null. And when we reject the null, we say, you know what? One is less than the other, or one is more than the other, depending which one went in first. And so we reject the null and we find that there is a difference. The reality is when you reject the null for a two-tailed test, initially, you don't really care if it's lower or less. You just ask to reject the null. Further investigation allows you to see what happens. Other things like when I know what sigma is, can I generate the same kind of statistic? Is food expenditure in City 1 more than City 2? So we have that information here. City 1, City 2. We know their sigmas. We know their sample sizes, where they're different. Just a quick hint. When you don't have the same, you pretty much know it's not going to be a paired difference if you're trying to pick them out. Just hint, hint. Now, in this case, mu1 greater than mu2. This will go in the alternative hypothesis because there's no equal sign here. And we know that it's going to be set to 0. So we have alternative hypothesis, we have the null hypothesis. We're going to create a z-statistic, pretty simple here, and let me float out here real quick and show you where I have this. We calculate z to be 1.85. Now think about what that is. If you think about z, one deviation either way puts 67% approximately within the center of z0. Two deviations puts about 95%. So you haven't really thrust yourself all that far out to be way out in the 2.5%er. So if that value were bigger than 2, then you'd say, wow, that's pretty impressive. Well, what we need to do is take that value and calculate it. So we want to know the chance we put that bad boy out in the right tail greater than 1.85. We're using the dist function here because it's a probability. And since we're looking into the right tail, we have to look 1 minus. That's stat 210 right there. How do we fly that right out there? As we calculate this thing, you get 3.22%. That's how that's calculated. That's less than 0.05 we reject. Now, we're not really, really far out for a two-tailed test, so we can reject that at an upper tail 5%er. Not a problem. Two means. How do you do it this way? We know the gold industry, we're looking for the annual return on these two values, and here's 10 observations. Is there a difference? 5%. Assume they're normal, assume they're unknown, assume they're unequal. Well, let's take a look at it. I'm able to take something like this. Here's golden oil, and I brought it over here. And I can run something, and I have an example like this out on Canvas. If I run the data analysis, and I want to know t-test, that means I don't know sigma, unequal variances, and I'm going to go in here and pull in gold, oil. I'm assuming that their difference is 0. I know there's not. And I'm going to kick in labels. Now I'm going to put the output right over here. Hit enter, and you get this wonderful thing. And you know from a one-tail perspective, has a really, really big p-value, and from a two-tail perspective, it's a huge p-value. So let's go back. In doing all this, we realized that getting such really large values, we're not going to reject the null. So that means we're going to find that they're equivalent. So over time, these two values, sample size 10, which is really too small to do anything with, we want bigger samples, but in this small sample case, it doesn't work. That's our problem. We don't reject the null, and we find this thing. So the last piece would be what we do with matched pairs. Matched pairs, much like anything else we do, a little bit different. Now I have an example that I have specifically out on Canvas. You can take a look on how to do matched pairs. This is nothing more than a simple t-test. And I'm going to take what I know from one group, what I know from another group, and take their difference, just like this. Let me find it here for you. So let's just say I have a before and after. Here's the before effect, here's the after effect. If I just take the difference between them, I could run this as a single sample t-test and get the same result as if I would run a two-sample test. But it's a before and after, so I can run it as a paired t-test. That's a t-test paired two-sample. You go in here, calculate the two, put it over here, and I get a result like this, where I have a p-value in a one-tail perspective of 5%, 5.5%, two-tailed 11. We want to make sure that there are at least 30, and again, we're not, and this is just for some, well, these are 30 for simplicity. Most often they're not, but this one is, so this does work. Sample size 40, it's important that they match up. And we can see from that in this case, since we aren't able to reject the null from the hypothesis of the two with matched pairs, what we found is between the two, there's no significant difference or no change occurred. You can do the same kinds of things as it's saying adjacent plots of land, and that's more when we see things. The best way to think of it is how somebody appraises a house and something like that. You could do confidence intervals. This confidence interval, you create this average of D. This is the average of the differences. So I could take the average of all the differences and get 2.1 and then float around that. This, what you see right here, is exactly what you would do for a general confidence interval for a t-value single sample that you had in Stat 210 using t, in this case t-inv. You would do t-inv, you would use two-tail, put your full alpha value in, and then multiply it by the standard deviation divided by n. That's square root of n. That is your standard error. All kinds of tests are the same. Two-tail, upper tail, lower tail. And your statistics look exactly the same. I'm just killing it now with all this information. So again, I'm going to keep putting more stuff out there. Hope this is helping. Keep looking, keep reading, send me emails. Again, I'm thinking about moving the office hours a bit to help everybody out because it seems like we're spread out all over the place. Try to move maybe to Thursday night and see where it goes. All right, I'll catch you with Chapter 11 here in a bit.